Hi everyone, welcome to this session on privacy by design for JavaScript data systems. I'm excited to share how we can build secure and compliant architectures that respect user privacy while maintaining full system functionality. Allow me to introduce myself. I'm Chittireddy. I'm a data engineer at Meta. I specialize in privacy-centric data architectures and real-time data streaming systems. I spent many years at Meta building architectures and systems that are privacy aware, both in data infrastructure and data processing. Today in this conference, we're going to explore the critical intersection of privacy, compliance, and modern JavaScript data engineering. This is not just about following regulations. This is about fundamentally rethinking how we architect our systems. And as a quick disclaimer, what I'm about to share is in no way a reflection of how we build systems at Meta. This is purely out of my experience in building data systems that are privacy compliant and privacy aware. Without further ado, let's get started by talking about why this matters. Currently, we have about 140 countries which have strong privacy regulations. And the average cost of data breach is in the millions, about $5 million in 2024. And that's a pretty high price for any firm to take on. And the scary part is, out of the data that was lost or that was stolen, 87% of US citizens can be identified using simply three attributes like zip code, date of birth, and gender. And this is not some theory. This is actually happening right now. And privacy is no longer optional. It's a technical and business requirement for any modern Java data script system. So what exactly is privacy by design? It's a proactive approach that embeds both privacy protections into the system architecture from the ground up and privacy compliance. And for JavaScript developers, this means integrating privacy controls through the entire data engineering lifecycle. From the moment data is collected on the client side, through the storage in Node.js backends, all the way to processing and analytics. Privacy must be baked in at every step. There are four core principles that I want to discuss. The first thing is proactive and not reactive. We anticipate and prevent privacy issues even before they occur. The second one is privacy as a default. We choose to set in maximum privacy controls in the system architecture automatically without user intervention. We do not expect them to come and choose that. We would rather want to enable that from the get-go. The third thing is privacy is embedded into the design itself. As you get started with the design of the product, that's when you start thinking about privacy. And it's not an afterthought. It's not something that you add on at the tail end, because we all know that doesn't scale. And finally, full functionality, because we're all passionate developers and engineers and architects, and we don't want to compromise the product functionality. So we'll be talking about how to do this privacy centric as well as keeping full functionality, keeping the product usable. Let's dive into some concrete techniques. The first one is k-anonymity. K-anonymity ensures that every record in your dataset is indistinguishable from at least k-1 other records. Say if you choose your k to be 5, then any individual's data looks identical to 4 other individuals. And this prevents hackers or users from, when I say users, system users, from tracing back that individual and figuring out their demographic traits. And the other concept is L-diversity, which extends this by ensuring diverse sensitive attribute values within each group. So not only are the people grouped together, but each group has varied characteristics. So this is essential for healthcare data especially, or any sensitive protective data, where, for example, in healthcare setting, you wouldn't want all the patients sharing same medical condition in one group. If that group's data is lost, then that would defeat the purpose. So you want to scatter it all over so it's not easy to trace back to a specific individual. And next, how does this differential privacy look in practice? And differential privacy is where math gets very interesting. So we basically add calibrated mathematical noise to query results. So we ensure that the presence or absence of any single individual does not significantly affect outcomes. And epsilon values, this is a differential privacy concept between 0.1 to 1.0 give strong privacy guarantees while still maintaining statistical utility. If you go beyond 1.0, you might be adding too much noise and you cannot trace back. Between zero point 0.1 and 1 will give you enough salting into the data, and that will still keep statistical utility of the data. And the key insight here is that individual records become impossible to identify and aggregate patterns become clear or remain clear. And finally, for JavaScript implementations, we have libraries like Node Differential Privacy for Node.js that can implement local differential privacy directly in the browser. And this enables privacy-safe analytics without sacrificing the insights your business needs. The next type of privacy that I would want to talk about is pseudonymization and tokenization. Pseudonymization and tokenization are your bread and butter for handling PII. With pseudo-anonymization, you're going to replace identifying fields with pseudonyms while maintaining referential integrity for analytics. Think about replacing an SSN with an internal non-traceable ID that won't that cannot be associated back to a user if the data gets lost or gets stolen or gets accessed by a stakeholder who is not supposed to access that data. And tokenization pushes this further by generating random tokens that map sensitive data stored in a separate secure vaults. So this is even more secure. And the beauty is that your analytics pipeline never touches real PII. So basically, the analytical pipeline is running on those randomized tokens that got generated and lets analysts still derive meaningful results. But when you really have to access that, then you can bring that data for disease. You can bring that data and join that back to the tokens. And let's talk about some advanced technologies. For those who are ready to push boundaries, homomorphic encryption lets you perform computations on encrypted data without ever decrypting it. So imagine running machine learning models that maintain up to 95% accuracy while the data remains encrypted throughout. Secure multi-party computation enables multiple organizations to jointly combine their combined data without anyone seeing others' information. Think about something to the effect of blockchain. And these are actually being implemented today in healthcare and finance. And I literally wrote a paper on healthcare analytics through differential privacy and homomorphic techniques. Let's talk about healthcare because that's definitely an interesting case study. In one of the case studies that I had done, we had worked with a healthcare consortium that we needed to enable medical research across multiple institutions without any exposing patient data. And using JavaScript-based federated learning with differential privacy, patient records never left hospital servers. So ML models will train locally on encrypted data, and only differentially private model updates were shared centrally. And the result is a fully HIPAA and GDPR compliant datasets while enabling breakthrough research. And this was keeping data local and sharing only privacy preserved insights. And think about this in terms of the amount of research that can happen, the amount of change that can be brought about in sensitive areas like cancer research or other HIPAA protected categories where you do want doctors and hospitals to share their knowledge across organizations while still protecting data privacy. And you wouldn't want to share this data as it is. So this is where we've explored a concept, and I've written a paper on it, of how do you implement models locally in a hospital, but share that results, share the differential results, the hospital, the aggregates or the model results to the next one so they can build on top of it. Let's talk about one more case study, and this one is financial services. In financial services, we implemented another tokenization at the point of payment collection. So card details are immediately tokenized as soon as they are collected, enabling real-time fraud detection without exposing actual card numbers. So we basically tokenize that information and send it to the back office for quick real-time analytics using streaming pipelines. And at the same time, customer behavior analytics run on key anonymous aggregations, providing valuable insights while protecting user privacy. Imagine you're using a third-party company or to run analytics on your customer. You're sharing with credit score companies or anybody like that, where you do want to share your data, but you don't want to share it at an individual level. This is where key anonymization or k-means clustering or they come in handy. And if you create a cohort of 25, 50 people, that will protect your data while still giving you great insights into customer behavior and analytics. So let's talk about the architectural blueprint for implementing this. First thing is the layer one is data collection. So we implement consistent consent management and minimize collection scope and immediately apply pseudonymization using browser APIs. So right as you bring data, you're very cognizant of what you're bringing into the system instead of just bringing all kinds of data. The second layer is storage, and here where we encrypt all the data that is sitting at rest, and we are separating, identifying information into different databases. You have one that is like truly sensitive PII data that sits separately from the non-sensitive data, like transaction records or whatever that is, and you ensure that there are strict access controls that are delineating data across both systems. Layer three is processing, and you're applying differential privacy across all queries and using secure enclaves for sensitive operations. You're not just like running user level information, you're trying to aggregate key anonymization, k-means clustering, or any of these techniques that we have discussed so far. And for the analytics, you're only generating insights from anonymized data sets. You're going back to your storage layer two, where you're only extracting or using the data from the de-identified data. And you're maintaining comprehensive audit trails. And this really comes in handy, especially for one, if there's an unfortunate breach, or two, when you're getting a third party to certify your system, especially this is folks in banking and insurance, this is the best, and also healthcare. Layer five is access. You're enforcing a role-based access control system where you're ensuring that there is purpose limitations and you're managing your user rights thoroughly. And in this one, the most important thing is principle of least privileges. You don't want to give people access to data that they don't really need access to. And then let's talk about the JavaScript tools and patterns. For implementation, you've got powerful tools at your disposal. In Node.js, use the built-in crypto module for encryption and no differential privacy for implementing DP. Add JSON Web Token for secure token management. And on the browser side, you have a subtle crypto API for client-side encryption. You can implement local differential privacy before data leaves the browser and use privacy-preserving analytics SDKs, architecturally adopting privacy-first API design patterns, implementing zero-knowledge authentication where possible, and considering federated data processing to keep data distributed. This is definitely a lot of information on this slide that I went through, but you'll have access to this deck, so you can go back and reference it. And finally, let me wrap this up with common pitfalls to avoid. Firstly, logging PII in plain text. Your application logs error messages, debug output are often stored indefinitely and are searchable. One stack trace with user data can undo all your privacy works. Secondly, weak pseudonymization. Using MD5 hashes or sequential IDs isn't really pseudonymization. It's just obfuscation. These patterns are trivially reversible. And I'm yet to see a system where people don't confuse, or an organization where people don't confuse hashing with encrypting. They are traceable, they can be relayed back. And third thing is over collection mindset. Trying to grab every data on the get-go without figuring out a plan of how you plan to use it or how you try to protect it is a very bad precedent to start with. Think about it very proactively. Think about what you want to do with that data before you even collect that data, and be very methodical about doing this. Fourthly, implementing privacy only on the client side. Browser-based controls are important, but never sufficient. Any developer with dev tools can bypass them. So ensure that you're implementing both on the client side and on the server side or the backend side. And fifthly, ignoring data retention. Keeping your data forever, just in case, violates many privacy regulations, including GDPR, California Privacy Law. And not just only that, and in an unfortunate incident, all that data that's been sitting around that is much more expensive if an intruder gets access to that data. And the good thing is, all these things can be absolutely prevented with proper design, with the techniques that we have discussed on this presentation so far. And lastly, thank you for, one more slide, key takeaways. So let me leave you with 4 other key takeaways. The first thing is embed privacy early. Retrofitting privacy into an existing system is expensive and risky. Design it from day one. Second thing is layer your defenses. No single technique is strong enough. Third one, balance privacy with utility. Only extract data where you need and ensure that you're protecting whatever you're extracting. And fourth, stay compliant by design. Privacy by design principles naturally align with all the privacy laws out there like GDPR, CCPA, HIPAA, and a bunch of other regulations. And good architecture makes you compliant by natural effort and not as a burden. And finally, thank you so much for the opportunity for allowing me to speak with you. And I hope you took something valuable away from this conference and from this presentation. And good luck with you on your future endeavors. Thank you.